Let's talk about part 3, the sampling distribution. This is really an interesting conversation that we'll be having. Let's talk a little bit about the sampling distribution and sample error. What is that? Well, even if we have a random sample, a selected sample is only one of many possible samples that can be drawn from a population. So let's say we have 12 people, all right, in the class, and we take 4 people. That's our N for the sample. Well, there are going to be 3 other groups of 4. Are they going to be entirely the same? No, they're going to be different. One could be 2 women and 2 guys. One could be 3 guys and 1 woman. One could be people with long hair, different mixes. So you get it? So every sample is not going to be the same that we take from a population. And so what we're going to deal with is sampling error. And sampling error is the variability of the statistics, the mean or percent from a sample to sample, just due to chance, okay? How many redheads are we going to get in a sample? How many people from Connecticut are we going to get in a sample, etc. Okay, so we that's called our sampling error. Statistics observe for all the different sample distributions form a distribution referred to as the sampling distribution. Okay, so samples have their own distribution. You remember how we have a distribution in a curve? Well, samples have their own distribution. Okay, and the standard error of the mean, that is the average deviation of the sample means from the population mean, is called the standard error of the mean. It equals SE, which is the standard deviation times the mean, okay, standard deviation divided by the square root of n. All right, don't get too confused with that. Here's a clarification about the sampling distribution. It is important to understand that researchers don't actually empirically construct sampling distributions. SPSS does that for us. So don't get all glazed. Don't let your eyes glaze over, okay? SPSS is going to do this for us. When conducting research, researchers do not collect all the possible samples. I don't think so. That's going to be too hard. That's silly. We don't have the time, the money, the inclination, or anything else to do that. And remember, sampling distributions are used to make probability statements in inferential statistics. Example, all right, we want to get the average GPA, the grade point average of UNH students. All right, this is your population. You know that the average GPA of the total students is exactly 3.3. So let's assume that we got funding to conduct a study with a random sample of 1% of the population. All right, what means would you expect in your sample? What means would you expect if you repeated the study with other samples? They'd be different, right? I mean, not everybody, that's the mean of the population GPA is 3.3, but my samples could have other mean GPAs. How much variation of the means would you expect with a larger sample? Less, right? Because the larger the sample, the closer it gets to the population. And this brings us to the central limit theorem. Whoa, what's that mean? The characteristics of the sampling distribution are known as the central limit theorem. It's a fundamental mathematical proposition of inferential statistics, okay? And here it is. For any population with a mean and standard deviation, the distribution of sample means for sample size n will have a mean of mu and a standard deviation of the square root divided by the square root divided by the square root of the standard deviation, I apologize, divided by the square root of n, and will approach a normal distribution as n approaches infinity. So as that simply means the bigger the sample, the closer it's going to get to the population. It describes the distribution of sample means for any population regardless of shape. All right, mean or standard deviation. and the distribution of sample sizes approaches a normal distribution as the sample size increases. Got it? As the sample size gets bigger, it gets closer to the population. What does this mean? Each mean based on a sample deviates from the population mean. Of course, it's got to, right? Go back to that GPA. Not every group is going to have the same GPA. The mean GPA for the entire group was 3.3, but some groups are going to have higher, some groups are going to have lower. Some sample means are above and some sample means are below. Got it? With a large number of samples, the various means have a distribution themselves. It's called the sampling distribution. You got it? The various means have a distribution themselves. Okay, each sample is going to have its own distribution. That's called the sampling distribution. What does this mean? It means that the larger the sample, the closer the estimated sample mean is to the population mean. Where'd we hear that before? The larger the sample, the smaller the deviation of the sample means from the population mean. So it's going to deviate less. It's going to be closer to the mean. And the larger the sample, the more sample means approach a normal distribution, even if the population scores aren't distributed normally. And why is that? Because you're going to get more samples with the same distribution, whether it be normal or not normal, as your population. Okay, put it all together. What does it all mean? A statistic estimated on one single sample does not provide the exact value of the parameter in the population. Why? Because it's only one sample among many possible samples. Right? The larger the sample, the better chance that your estimated sample statistic is equal to your actual population mean. You got it? The bigger the sample, the better you're going to be able to infer. Check this out. Go over here to this URL, and it explains what we're talking about really nicely. Here's part 4. It's an introduction to hypothesis testing and significance tests. This is important, it's easy, and it's interesting. Okay, so Graviter and Wallnow tell us that a hypothesis test is a statistical method that uses sample data to evaluate a hypothesis about a population. The objective is to use sample data to draw inferences about the population of interest. So I have an idea, a hypothesis about a particular population. The logic underlying the hypothesis test is that 1, you state a hypothesis about the population. 2, you draw a random sample from the population, just like we were talking about before, the gold standard, the random sample. 3, we compare sample data with the prediction made from the hypothesis. If the sample data is consistent with the prediction, then the hypothesis was accurate. What does this mean? These are the steps how to do it. First, we start with 2 alternative hypotheses. Okay, the null hypothesis, H subscript 0, means that there is no relationship in the population between the given variables, okay, or no difference between a parameter and a specific value. So let's say that I say that I'm testing smoking and whether it causes cancer. My null hypothesis is that smoking does not cause cancer. Those are the 2 variables. The independent variable is smoking, the dependent variable is cancer, and my null hypothesis is that they are not connected. My alternative hypothesis, H subscript 1, means that there is a relationship in the population between the given variables. My independent variable being smoking and my dependent variable in this case being cancer, and I find that it does have a connection. So I apply the appropriate statistic that summarizes the pattern or associations between the variables. I describe the kind of relationship, positive or negative. Does smoking cause more cancer or less cancer? Is it positive or negative? The level of significance, which is the likelihood that this relationship actually exists, and the strength of the relationship. Okay? The null hypothesis means that no relation is detected, or the observation and parameter are not different. You either reject the null hypothesis or fail to reject the null hypothesis. We often say that we accept the null hypothesis, but that's not really correct. We fail to reject it. The alternative hypothesis, again, H1, when there is a relationship between the studied variables, okay, smoking does cause cancer. So H1 is the opposite of the null hypothesis. The alternative hypothesis, H1, must be true if HO, or the null hypothesis, is false, all right? It contains the conditions of inequality. All right, it's lesser, bigger, or doesn't equal. Here's an example. A medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is concerned with the pulse rate of the patients who take the medication. Okay, so we formulate a hypothesis to test whether the pulse rate will be different from the mean pulse rate of 82 beats a minute. Okay, my null hypothesis states that the mean is going to equal 82. There is no difference. My alternative hypothesis says that the mean is not going to equal 82. That's the condition of inequality, right? This is a two-tailed test because we don't know which way it's going to go, whether it's going to be less or more. So it could be under either tail of my curve. Okay, it could be under this tail or it could be under this tail. We don't know if it's going to be less or more. Here's another example. A chemist invents an additive to increase the life of automobile batteries. If this mean lifetime of a battery is 36 months, then here are the hypotheses. The null hypothesis states that it's going to be equal, less than or equal to 36, and my alternative hypothesis is the mean is going to be greater than 36 months. Okay. This is a one-tail test because we're interested in a mean lifetime that's greater than 36. So if you draw your curve, okay, we are only working under here, this tail. We're looking for ones that are greater. Here's another example. A contractor wants to lower heating bills by using a special type of insulation in homes. If the average monthly heating bills is $78, the hypotheses about heating cost are, come on, you tell me what they are. What's the null hypothesis? The null hypothesis is that it's going to be greater than or equal to $78, and the alternative hypothesis is that the mean is going to be less than $78. Okay, and this is a one-tailed test because we're only interested in reducing the bills. Here's an example of a hypothesis in the criminal justice system. Defendants are presumed innocent until proven guilty. Okay, so the null hypothesis equals the defendant not guilty. The alternative hypothesis is the defendant is guilty. Just like an individual is presumed innocent until strong evidence of guilt is presented to the judge or jury, in research, the null hypothesis, the one that means no relationship, is assumed to be true until data shows us that it's not. Other examples with other statistical tests. Okay, and we're just going to pop over. We're at 13 minutes, so I want to pop over to the next tape. It'll be a very short one, so bear with me.